we would like to evaluate the following line integral. Now, because it's a closed loop, it turns out it doesn't actually matter where we begin because we're going to end at the same place. So if we chose to begin here, we end here. If we begin here, we end here. One of the things we always do, though, is we keep the region to the left as you're moving around, which essentially means you're always going to travel counterclockwise. Think of a circle when you're doing things in polar. You do the same thing. So I want to use Green's theorem. I can set this up as two separate line integrals, do two separate parameterizations. It wouldn't be terribly difficult, but it would be rather long. So if I'm going to use Green's theorem, what I want to find is the partial of n with respect to x minus the partial of m with respect to y. So if this is m and this is n, then what I'm looking for is the partial of n with respect to x would be 4y. The partial of m with respect to y would be 2y, and that's simply 2y. So I'm going to do the double integral of 2y, either dy dx or dx dy. Now, looking at my region here, probably simplest to just go ahead and use vertical rectangles, this being y equal x squared, this being y equal 2x. So we will do the double integral, where y will range from x squared to 2x, x will range from 0 to 2 dy dx, which will simply be 0 to 2 of y squared from x squared to 2x dx. When I substitute 0 to 2, 2x quantity squared, x squared quantity squared, which would be 4/3 x cubed minus 1/5 x to the 5th evaluated from, in this case, 0 to 2, and that would be 64/15. A fairly simple process once we changed it to a double integral. Now let's consider the following line integral. This one a little more complicated than the previous one, and this time I'm going to be going over the square with the following four vertices. And again, because our orientation must leave our region always to our left, we would go in this order, but it would not matter which one you did first because you would essentially be adding four line integrals in the end. Not a complicated problem, but a very long problem because four separate line integrals, four separate parameterizations. So again, we will use Green's theorem. So our first step is to find nx minus my. So again, this being m, this being n, the partial of n with respect to x is 4. The partial of m with respect to y would be -2, and that would give us 6. So we're going to integrate 6 over this square region. So the value of our integral will be 6. Now we can go dx dy or dy dx, it won't matter. So let's say this time we decide to go dx dy. Well, both x and y will have constant limits of integration because it is a rectangular shape. So after one integration, 0 to 4, 6x from 0 to 4 dy. That will give us the integral from 0 to 4 of 24 dy, which is simply 96. Where this would have been a fairly complicated problem, once again, this was fairly trivial. Now let's look at the following. This very complicated problem, I have a circular region, so the usual parameterization here, I would choose let x equal 8 cos t, let y equal 8 sine t, but now I've got trig functions of trig functions, e raised to trig functions. This would be a nightmare to do as a line integral. But if we choose to do this using Green's theorem, again, that being m, that being n, always remind yourself, the partial of n with respect to x is -2x sine y. Notice the partial of m with respect to y is also -2x sine y. So nx minus my in this case would be 0. But that can only happen if the original force was conservative. So that means the answer to this question, this is equal to the double integral over the region in the xy plane of 0 dA, which is 0. Now that's kind of curious. But notice, if conservative, that means our integral is path independent. Path independent means it does not matter the path, just where you begin and you end. So if I'm going on a large loop and I end exactly where I began, then the displacement is 0. So if I think of my force vector, again, that's m and that's n, that means in this problem my force vector would be mn. This tells me my force is conservative. That means there was a potential function which I can find through integration, but the beautiful thing is, because I begin and end at the same place, the integration will always produce 0. This is considered the most important type of problem. So Green's theorem will tell me if I have a conservative force, I will get 0. Now usually a line integral, you begin one place, you end somewhere else, and there's no shortcut to that problem. But on a closed loop, when using Green's theorem, I sometimes am fortunate enough to get a 0 because I had a conservative force.